Okay, we'll get started. Am I still coming through here? Did something happen? Okay, sorry. Oh, too loud. All right, so we'll cover a few topics today. Let me see. Oh, sorry. Okay, so we left off on Tuesday. We talked about a few root finding methods, and I'll cover one more root finding method, and this is called fixed point iteration. This is like the first one that the book covers, but it's the last one I'm covering here. Okay, so this is one more root finding method, and this one is called fixed point iteration. Okay, and a fixed point of some function. So if you have some function g, okay, a fixed point of g let's say a fixed point, A is where g of A is equal to A itself. All right. So basically, it's where the function intersects the line x equal y equal to x. Okay. So effectively. G of x equals well, yeah, basically you've got some function and some diagonal line. Okay, not some diagonal line. This is the line y equal to x. And if you have a function, whatever it is, okay, this is a fixed point. And this would be a fixed point. So, okay, these are all fixed points here. Okay, because at this line, at this location, we have x, and it's also equal to y is equal to x right there, and g of x is equal to x. Okay, these are also another fixed point. And the way a fixed point iteration works is that all you do is you just take some function or some value, you plug it in, and then whatever that thing spits out, you plug that back in. Okay, so you just some starting point. Let's say x0. Okay, you plug it in, and then you get g of x0, and you're going to set that equal to x1. Okay, and then all you do is you just repeat, and not always, but a lot of times, okay, and you just basically plug this in, etc., etc., etc. Okay, and then you might come to a point. So I'll draw it on another slide here. it might come to a point where you get into this kind of this loop where g of, we'll say, xn ends up being xn, okay? So after many iterations, you can end up with something like this, where what you're plugging in ends up being spit back out, okay? It doesn't happen all the time, but it does happen often enough for this to become a somewhat reliable method. Okay, so let me just kind of draw a little picture of what this thing kind of looks like. Okay, so let's say we have something that looks like this, and then we'll bring this. This is, yeah, that's fine. Okay. Okay, so let's say I start right here. Okay, so this is x0, okay? I come up to here, right? And this is the height right here. I'll put it in green. This is g of x0, okay? And so whatever this value is, okay, this is going to become my new x1. So where g of x0 is, this becomes x1, which is equal to g of x0. Do you guys see that? Okay, and then I find, okay, well, what is g of x0? G of x0 is right here. Okay, and I come over, I'm sorry, this is g of x1. Okay, and this location now becomes my new x2. Okay, and then I just repeat this, and I keep kind of stepping over until I run into that, and then we go down. And you can see if I continue to iterate, eventually we're going to end up at this location, right? After several iterations, we will end up right here, which is the fixed point. Okay, so with each iteration, we you know, wherever we start, we're going to go, and eventually we end up at the fixed point of g. Okay, so we will find, so this is g of x over here, and this is y equal to x. And if we come up to here and we go over there, we will end up at the fixed point right there. Okay. All right. So how does this become a root finding method? Okay. So it's really like a very simple algorithm. The algorithm is the value that you're going to use at your next iteration is just take your current location x, plug it into the function, and then whatever you spit out, that's going to be the thing, okay? The next value you use, and then you just repeat until the difference between xn plus 1 is almost equal to xn, okay? The difference between these is very small. So generally you just do a tolerance factor, okay? And you go there, okay? So with fixed point iteration, let's say you want to find the roots of some function. Well, all you do is you just rewrite the function that you're looking for into the form where you can do a fixed point iteration, okay? All right, so to use using using fixed point iteration to find roots, okay? Basically, so let's say you just rewrite the function to look like we'll just say rewrite the function g of x, or we'll say f of x equal to 0, okay? Because this is what we want to be g of x equal to x, okay? So this is what we do. So if we want to find the roots of this thing, we want to find where f of x is equal to 0, we just have to rewrite this thing so that it looks like g of x is equal to x, okay? And then we find the fixed points of this, and the fixed points of this will be the roots of this, okay? So we want the roots of f of x. F of x, and then just after some algebra, okay, we have g of x equal to x, and then the fixed points of g of x will be roots of f of x, okay? So it's as simple as, okay, kind of like your simplest case would be f of x plus x is equal to x now, and then so if you just say, well, g of x is equal to f of x plus x, you can find the fixed points of this thing, and that would be that would work, okay? But sometimes, unfortunately, fixed point iteration doesn't always work. This is one simple method, okay? But you might want to solve for other things, okay? So here's an example, okay? So example, this is from the textbook. F of x is equal to log being, whenever you see log in stats, it's always natural log, okay? So here, what they're doing is we want to find, okay, so one possibility is we go log x is equal to exp of minus x, and then we exponentiate both sides. We do e to this and e to this, and we get x equal to exp of minus x. Okay, and now this works as a g of x equal to x, and we just find the fixed points of that. That's one possibility. All right. Another possibility is we could subtract each side from x, and we would get x is equal to x minus log of x plus exp of negative x. Okay, and then this is x, and this works as g of x. Okay, there's all sorts of possibilities, and some of these will converge and some will not, and you just kind of have to play around with it to use this to find roots. Okay, so this is fixed point iteration for finding roots. The idea being the fixed point is where g of x is equal to x, and if you want to use that to find the roots of some function f of x, just rewrite it so that f of x equal to 0 is in the form g of x equal to x. Find the fixed points of g of x, and those will be your roots of f of x. Is that okay? Are there any questions on fixed point iteration? Okay. All of these root finding methods can then be turned into methods for optimization. Okay, and in our class, in this class, we'll just cover unidimensional optimization. In 102B, I cover multidimensional optimization. But in this class, we'll just start off with the basic ideas of unidimensional optimization. Okay, so we've covered root finding, and then now we'll cover optimization. Okay. The idea behind optimization is finding either the maximum or the minimum of a function. And in statistics, there's all sorts of applications of this. One of which would be maximum likelihood estimation. In that case, you find the likelihood of your data. Okay, right? So let's just talk about some applications. Okay, one is MLE. Okay, maximum likelihood estimation. Have you guys taken 100B yet? Yes, maybe, no? Okay. Or have you heard of this term, maximum likelihood estimation? Yes? Okay, I've got a few thumbs up. All right. And you might have done this mathematically, okay? The idea here is, you have data, okay? And then what you do is you find a function of the likelihood of your data, right? And the function itself is a function of parameters. Like, what is the mean of the population or something like that, right? Okay, the function is a function of parameters. Function of parameters, and the data is treated as fixed. And with maximum likelihood estimation, you're asking, what is the set of parameters that gives me the greatest likelihood of the data I observed? Okay? What is the or what is the parameter value that gives the maximum likelihood of the data that I have. Okay, we're and this was probably done in 100B, or will be done in 100B if you haven't taken that yet. And you know, if let's say you've observed a bunch of data and you want to know, okay, we're going to assume that this data comes from the normal distribution, right? Except we don't know the mean of this normal distribution. We don't know the standard deviation of the normal distribution that we observed this data, okay? So, the data, I've got these data points. Okay, if we're assuming it all comes from the normal distribution, what is the mean and standard deviation of some mystery normal distribution that's going to maximize the likelihood of the data that I have, right? And probably in 100B, you proved that the maximum likelihood estimation of that thing would be the mean will actually be the mean of your sample, and the standard deviation will be the square root of the non-normalized variance or something like that. Okay, so that's one possible application, maximum likelihood estimation. Another application of optimization is minimizing the total squared error. Okay, so a lot of times you want to know how good does your model fit the data, okay? And you're going to say the best model is the one that minimizes my root mean squared error or something like that, okay, right? RMSE, right? We want to try to minimize. So this is application 2, the root mean squared error, right? So we'll say the quote-unquote best model for the data I have will be the model that minimizes mean squared error, something like that, okay? So, you want to find the parameters of your model, the settings of your model that will minimize this thing, okay? So these are both applications of optimization. One, you're trying to maximize the likelihood. The other, you're trying to minimize the error of your model. And you might be able to do these things mathematically, okay? Maybe you can use calculus to maximize or minimize the thing, okay? And if you can, that's awesome. But a lot of times, the thing that you're dealing with, it's really messy, okay? It's a mess. And so numeric optimization methods help us, right? We don't have to worry about the calculus and stuff. Although one of these methods, involves calculus anyway. But sometimes we want to just find the maximum or the minimum. So, the things that we're going to learn will probably be done from minimizing, but minimizing and maximizing a function, they're exactly the same thing, okay? If you have a method to minimize a function and you want to use that same method to maximize it, what do? You just multiply the function by -1, and then you minimize that function, and the minimum of that negative of the function will be the maximum of the original function, okay? So there's no need to find like a reverse version of the function, okay? All right. Okay, so I'll just start off with most of our algorithms. find the minimum of a function. Okay. That they can be used to find the maximum too. All right, so let's say if we want to maximize f of x, we can just minimize -1 times f of x, okay? And there you go. All right, so let's talk about, I'm going to just cover two methods in our class. There's lots of other methods, and so here we'll cover just unidimensional. Well, I take that back, okay. I'm going to teach you just unidimensional minimization or optimization, and then in your homework, you will expand the concept of unidimensional to like a two-dimensional case, all right? Coordinate descent, all right? Okay, so we'll start with the unidimensional case. Okay, unidimensional case is pretty easy, and technically, we have a few methods. One will be Newton's method, and then we'll have a golden section search. Okay. All right. Newton's method. Okay, so we have Newton's method for root finding. And all we're doing is we're just extending this into optimization by saying if we have the derivative of a function, the roots of a derivative will be critical points, and we can evaluate those to decide if it's a minimum or a maximum. Okay? And technically, any of those root finding methods that we covered earlier could be used for optimization. You just find the roots of the derivative, and those will be critical points to evaluate. As long as your function is differentiable and as long as it is continuous, right? So technically, all root finding methods can be made into optimization methods. Okay, all we do is we find the roots of f prime of x, okay? All right, and the roots of f prime of x will be critical points. Okay, it's where the derivative is equal to 0, and so and they could all be either minimums or maximums, okay? Well, I should say local minimums or maximums, okay? And that's basically it, right? You've got some function. If you have some function f of x, and it looks like this, then f prime of x will be oops, will probably look something like this. All right, And then, okay, so this location, so the root of f prime of x corresponds to, this is where f prime of x equals 0. This is our local minimum. Okay, and we learned this in calculus, right? So, that's basically it, right? So Newton's method, what do we do? Newton's method for root finding. Okay, so let's say we want to find the roots. We'll say h of x, okay? Then the algorithm goes like this. What is that? You have some location. Oops. If this is x of n, okay, the next location is going to be x of n minus minus where the thing crosses over, right? We got to go over this distance here. This is technically our run, and this is the rise, and so it's going to be x of n minus the rise divided by the slope, okay, which is going to be x of n minus h of x sub n divided by h prime of xn. Okay, that's what it was for root finding. Okay, so now if we want to change this into Newton's method for optimization, okay, all we have to do is we just say Newton's method for optimization of, let's say, g of x. Okay, let's say we want to optimize g of x. This is equal to, well, we will let h of x equal to g prime of x, okay? And now, Newton's method for optimization of g of x is the same as Newton's method of root finding for h of x. Okay, so all we have to do is, the algorithm is now x of n plus 1 is equal to x of n minus h of xn divided by h prime of xn, which in terms of g of x is xn minus g prime of xn divided by g double prime of xn. Okay, and this will get you to a local minimum or maximum. Okay, and that's it. That's Newton's method for optimization. And technically, if you wanted to use any of the other root finding methods on a derivative, that works as an optimization method. Okay, the Newton's method for optimization, people just like it just because it's a very simple switch, right? The only requirement, the only thing that makes Newton's method for optimization sometimes not the best method is that it requires the function to be twice differentiable, right? You need to be able to take the first and second derivatives of the function. Okay, so you must be able to take first and second derivative of g of x. Is that good? All right. I wrote some code, or not. Actually, I didn't write some code. I just copied the code in the textbook, and it's good. All right. So here, this is like, how does the function work? Okay. So here we've got some function. The function that we are going to try to optimize. This is the function. Technically, what's this? Sorry. Apologize. Let me, I apologize. Let me. Okay. Where were we? Okay, so this is the function. Technically, this could go in right here. So this is not that. Here's the plot of the function that we are trying to either maximize or minimize. And when we run this function gamma.2.3 and we run it, what's going on here? Okay, and if I run it on some, you'll notice that if I plug in a value, it's going to give me three values. One is the value of the function itself. This is the value of the first derivative, and this is the value of the second derivative. Okay, and the function Newton as a method for optimization will use each the three values. So this returns basically the function, its derivative, its second derivative. And the way the algorithm works, you can see it work here, is just take the current value of x, subtract off basically the second divided by the third, which is subtract off the first derivative divided by the second derivative, okay, which is exactly what we have here. Value of x minus the first derivative divided by the second derivative, right there, okay? And so that's what we have. And basically, it just continues doing this. It runs it in a while loop, and the while will stop when this is no longer true, when the difference of these things is smaller than some tolerance, or you've reached the maximum number of iterations. Okay, and it should be easy to kind of follow this, and we can see the function work. So if I apply this right here, so here's the function itself, here's the derivative of the function, and so we can see we're going to have critical points at 0 and 1, and when we start off at 0.25, it pretty much goes to 0, and that's going to be the local, like a local minimum when we look at the original function. And then if we start at another place, it finds a critical point 1, which is going to be a local maximum. Okay, for Newton's method there. All right, is that okay? Newton's method for optimization. It's just an application of Newton's method for root finding, but now on the derivative of the function. And any method that can be used for root finding, if you can apply it to the derivative, can also be used for minimization or maximization. Okay, and then we have another method, and this is called the golden section search. And I will link a very good video. There's like The golden section search is a kind of a purely numeric method. There's no derivatives, and it works off of the idea of the golden ratio. All right, so do you guys know the golden ratio? The golden ratio is, let's see, you've got this rectangle here. You've got, if this is 1, 1, and x over here, basically, if you take off a square, the remaining rectangle has the exact same proportions as the original rectangle. So that means 1 over 1 plus x is equal to x over 1, okay? So the proportions of this little leftover rectangle has the same proportions as the original rectangle, right? And then this, like, I don't know, the little rectangle has same proportions as big rectangle. And so a nice property of this is that if I don't know where I'm drawing these, okay? But let's say I go from 0 to 1 here, okay? And the golden ratio is around, 0.618, we'll say, okay? 0.618. And so if I go, 0.618 that way, and then I go the opposite direction, so 1 minus 0.618, which would be 0.382, all right? About that much, okay? One nice thing is that, let's say the ratio between 0.618 to 1 is pretty much the same ratio as 0.382 to 0.618, okay? So, this distance, if I just took this and I just stretched it out, it's effectively the same as from here to here, okay? These have the same ratios. All right, and vice versa. Going the other way, it works out as well. Okay, why do we want this? Well, this technically cuts down on some computational time here, in that we only have to do a few calculations here. Okay, this is what we do is we're going to use kind of the fact that this golden ratio holds up in to help us find a function's maximum or minimum, okay? So let's say we've got some function like this, all right? And this is bounded on the left and right here. So I've got, we'll say this is x left. What are the, let me just use the same letters. Yeah. Okay, it doesn't, I just want to use the same letters that the textbook uses, but they don't have good letters. Okay, so we got x left and x right, okay? And what we're going to do is we're going to find basically the spots according to the golden ratio here, okay? And so, I'll call this, do these have letters? Okay, I'm just going to call these J and K, because I don't know where the book is. Okay, and basically K is equal to XL plus the golden ratio times the difference between XR minus XL, okay? And then J is XR minus the golden ratio times XR minus XL, okay? So this is, you know, effectively 0.618 of the way to XR, and then J is 0.618 of the way from XR to XL. Is that okay? And what we do is we evaluate, so we find basically the two spots where the golden ratio goes, okay? So, you know, J, find the two spots determined by the golden ratio. Okay, and then you evaluate, find f of j and f of k. Okay, and then you say compare f of j and f of k, right? And if f of k is larger than f of j, which is what we have here, okay? So in our case, f of k is larger than f of j, all right? So what that means is that the minimum on our interval cannot be between f of k and x of r, okay? Because we know that there has to be, the smaller value is on this side, okay? So we can eliminate this side, okay? We know that a smaller value exists between XL and K. So the hunt for the smallest value can ignore basically K to XR. Right? So we can eliminate this. And so now we're going to take this piece, all right? So K becomes our new becomes the new XR. Okay? K is going to become the new XR. And the advantage of using the golden section search by using K as the new XR, J becomes what? The new K, right? And I don't have to find two new locations and recompute f of j here. Okay? K becomes the new XR, and J becomes the new K. Okay? And we do not have to recalculate those values. So let me just copy that down, all right? So what happens is we scribble that out. This is now XR, this is K, and now I find a new J. And then I compare that, and we can continue. And we can decide whether or not to keep this one or this one, and so on and so forth. And then we repeat. Okay. So the golden section search you start off with some interval. You calculate two values within the interval to decide, is it going like this or is it going the other way? And then you repeat it over and over and over again, right? So maybe we eliminate this side and whatnot. Is that okay? All right, and so that's golden section search. I have it coded up here. I actually just looked online and found somebody else who wrote it up for me, which makes it nice. Okay, and so the way the arrangement of the points in this thing is that we have the lower bound. We don't call it j, we call it x2, and we don't call it k, we call it x1, and we have the upper bound, right? And so the golden ratio is 0.618, something around there, a little bit off, and we do lower plus the golden ratio and upper minus the golden ratio times that difference. We evaluate the function at those points, giving us basically f of one of those values, x1, and f of x2, and then we just say, is f2 bigger than f1, or is it the other way around? And then depending on that, we assign either x2 to become the new lower bound, or x1 becomes the new upper bound, so on and so forth, okay? And all we do is we just put that in a loop until the difference between the upper and lower is smaller than some tolerance, and then at the end of that, we just return halfway between the lower and upper bound, okay? So I think this code is very clearly written. I hope. I took Eric Kai's code and I just added all of these comments to try to make it as clear as possible. And we run that, okay? And then so if you have some function, let's say we got f of x minus 3 quantity squared, and here let's just do x being a sequence from 0 to 10, and we'll say length out is equal to 200, and we'll say y is f of x, and let's plot x versus y, type equals L. Okay, so this is what our function looks like, and we can say, okay, run golden section search, and it says, okay, the minimum I found is at 3.00001, okay? Which is a little bit off from the true value of exactly 3, but it's pretty close, right? And so, whatever function we have, if I do this and I plot this, my minimum is at 4.2345. Let's see how well golden section search works, and it actually found it exactly, that's good. Okay. All right, let's just try this one. So here's another function, okay, and if we want to maximize this function, we're going to have to use 1 minus that, okay? So I'll have f3 be function of x, and it's going to just return minus 1 times f2 of x, okay? And then we'll use golden section search on this, okay? And it's finding the minimum of the negative, or the maximum, to be very close to 1.999995. Okay, so this is just golden section search, and you can always, right now the tolerance is 1e minus 5, but you can change it so that the tolerance is even smaller, and then it's going to take a little bit longer. Okay, but here now the tolerance with a lower tolerance, maybe it runs a few more iterations. It's getting values that are pretty close to the actual values here. Okay, So all of this code has been posted online. You can read through it and make sure you understand the golden section search and the Newton's method for optimization. Okay. I haven't posted homework 4, but I will probably today, and it will involve what's called coordinate descent, okay? And I'm going to just describe coordinate descent here, and it will be your job to implement a coding algorithm for coordinate descent, okay? So, and I'm giving you the simplest case, which is the two-dimensional case, but technically coordinate descent can be used for, higher dimensional data. And the idea is this, okay? Let's say you've got a two-dimensional function. Okay, and so, with a two-dimensional function, how do I do this? I've got this, and I've got this, and okay, so we've got this thing, and with a two-dimensional function, you've got something that looks like, I don't know how to draw. How do you draw a surface, right? So let's say you've got kind of a, what is this called? A paraboloid? It's like a bowl, right? This is the worst picture ever, but we want to minimize this thing that right here, okay? If we make a contour plot, it might look, depending on the way it looks, maybe it looks like this, right? Okay, and with the minimums being somewhere in this zone here, right? This is so imagine like it's supposed to look like a bowl. Okay, so we have a a bowl-shaped function, and this is a contour plot, and we want to either maximize or minimize this thing. So we want to find the minimum. In 102B, I teach gradient descent, which is basically uses derivatives, multi-dimensional derivatives, a gradient. In this case, we'll do coordinate descent. Okay, and the way coordinate descent works is, if we've got, we'll call this x1 and x2. Rather than trying to minimize both x1 and x2 at the same time, it's going to just minimize one function at a time, okay? And so, can I draw this? So, let's do a coordinate descent for optimization. Okay. Oh, maybe this is what I want. Oh, look at that. Thanks, sketchbook. This is about as good as I could hope for. Okay, so we've got this thing, and basically all we do is we just start off at some spot here. Okay, we have x1 and we have x2. Okay, and we just let's say, okay, so we have the function of x1 and x2, and what we do is we just pick some arbitrary starting values. Okay, so let's say I start at this location. Okay, so this will be my start location. And so this will be x1 at time 0 and x2 at time 0. Okay. And then all we do is we just rewrite, we lock in one of those values. All right, and so we say x1 maybe and then we lock in one of those values and rewrite the function to be a function of one variable only. So I'll lock in, so in this case we will lock in x2 to equal x2 at time 0, all right? And so now I have f of x1 given that x2 is equal to x2 at time 0, all right? And basically, I'm going to search along this path right here. So this is, x2 is locked in at this value. And we minimize this function. We find x1 that minimizes f of x1 given x2 is equal to x2 at time 0. Okay. So where's the minimum? The minimum is probably going to be somewhere around here. Okay. So now we have x1 at time 1, okay, and then we lock in x1, and then we minimize, we rewrite f, and so we have f of x2 given x1 is equal to x1 at time 1. Does that make sense? And so with that, I will search along this path, and I try to find the minimum, the value of x2 that minimizes this function, right? So each of these things, when we lock in, this is a two-dimensional thing, but when we lock in one of these things, effectively, it just becomes a one-dimensional function. Everything else is held constant. Now it's just a function of x2 only. Okay, so we find x2 that minimizes this function. Okay, or argument here. And so that takes me to right there. And now I lock in that value, and then we're going to find the value that minimizes this. And that will probably be right here. We lock in that value, so on and so forth. And will probably get us pretty close to the minimum in a few steps. Do we have questions on this? So at each step, you're taking the multi-dimensional function. In this case, there's only 2 dimensions, so it's easy. But it could be expanded to other things. And at each step, you basically hold everything a constant, except that one thing, okay? It's kind of like when you're doing derivatives and stuff in multidimensional calculus. When you're taking partial derivatives, you just treat everything else as a constant, right? It's kind of like that, except you're not doing any derivatives. You're just treating all of the other values as a constant. Now you have a function of just one variable where everything else is a constant, and you try to find the minimum of that one function where everything else is a constant. Okay? When you do that, it will basically just find the minimum along a certain path where only that one variable is allowed to change. Everything else is held constant, okay? So you're just kind of, you know, in a two-dimensional case, when you hold the other variable constant, you're allowed to just travel along a path that's either parallel to the x or the y-axis, or horizontal or vertical axis. If it's a three-dimensional case, you know, and you hold the other two variables constant, then you're just searching along kind of a, you know, a plane or something. No, you're also just searching along a path there, okay? And so, you know, all these cases, you're just searching, you're finding the minimum. You lock in that minimum value here, and then you search along the next one, okay? And so it might take a few steps. If coordinate descent will take a long time if you've got really skinny, if your thing looks like this, it's like really skinny, then it could take a long time. But you know, it does a pretty good job a lot of times. Yes.
You find it like rounded, or just like if it was shaped like a U,
like a.
and does that mean that it would not constantly home in along one variable being fixed?
So if you have funny shaped things, it will still work. It's just it might take a long time to get there. Okay. Because
you don't need to like make adjustments for it. It will still work.
Yeah. It just I mean, all of these things, there's a caveat that maybe it doesn't work, okay? So none of these optimization methods are guaranteed to work in any case, okay? But most of the time, they work, okay? And it's just, it's kind of like, I don't know. You could imagine having like a topographical map of Los Angeles, and you want to find like the highest point. Okay, if you can search the whole topographical map, you might be able to find it very easily. Could you also do it just by driving on streets? Probably also. It might take you a long time, or at least you'll at least find a local maximum. Okay, in that you just drive, and then you just kind of looking along, you say, okay, well, you know, am I going up a hill? And then when you reach kind of the top of a hill, you can kind of turn on a street left and right. And you can imagine trying to, you know, imagine there's no traffic and you can do this. You can imagine trying to search for the maximum just by walking along streets, right? And if you were not constrained, you could just look around and say, okay, well, this looks like it's the kind of the steepest way, so I'm going to go this way. But if you're limited to just going either, you know, north, south, or east, west, you can still do it. It might take a little bit longer, but it can be done, all right? And that's kind of what we're doing. And yeah, if it's this funny shape, perhaps it'll take a lot longer. Perhaps it will fail. But the coordinate descent algorithm it's a good algorithm, okay, in trying to find local mins and maxes. Okay, so you'll have an exercise in your homework to do this. All of these things, pretty much you can. I'll find Wikipedia articles also that you can that give nice little summaries of these things. I think they're also described pretty well in your textbook, the scientific programming using R and whatnot. Okay. Okay. I'm going to cover briefly. We'll see how much I can get through this. Okay. this is where the compressed schedule, works against us. In that, I'm going to try to cover a little bit of ggplot too, okay, with graphics in here. So, because in your homework, I'm going to ask you guys to produce some plots, and I recommend using ggplot to make your plots here, okay? So we'll take a quick look here. We'll see how much we can get through. These notes are also posted online, so you can look through them in your own pacing. And then the textbook, or the book by Winston Chang, the R Graphics Cookbook, is really an excellent resource, and I recommend you guys to check that out. Okay. All right, so when we're talking about ggplot2, the GG stands for Grammar of Graphics, which is a system created by Wilkinson, and it gives this very structured perspective on how we should visualize data, okay? It's not the ultimate system for doing graphs, okay? A lot of times it's just faster to do a few things in base graphics. You saw me just do things using plot, X and Y. And for quick things like that, base graphics is excellent, okay? However, ggplot does a lot of beautiful things and allows you to make changes to kind of the structure of your graph relatively easily, okay? All right. So in a data graphic, what we have is we map properties of the data to visual properties in a graphic. That's the whole idea of data visualization. We've got properties of the data, and we are mapping them to visual aspects, right? Data properties are usually either a numeric or categorical value, and visual properties are things like the X position and the Y position, the color of the lines, or the height of bars, and things like that, okay? If we're not mapping data to visual properties, that's not a data visualization, okay? It says, on the surface, representing a number with an X coordinate may seem very different from representing a number with a color of a point, but at an abstract level, they are the same, okay? So when you create a scatter plot and you are representing the value of X for its X position, it's no different than graphing X using a different color, okay? You are just mapping the property of the data to a visual scale, okay? And in one, it's a spatial scale, and the other is like a color or a hue scale, okay? So at an abstract level, we're doing the same, okay? And that's where we're kind of starting here, all right? And that's the central idea of the grammar of graphics. Okay, so anyway, this is, let's say you've got this data. You've got A1, A2, A3, B1, and B2, and this is this, and we can plot this. If our data is set up like this, we can plot it, and we can just do bar plot, simple dat, and it does this, A1, A2, A3, and it plots, it says A1, we've got a height of 10 and 9 for B1 and B2, 10 and 9. And then for A2, whoops, we've got 7 and 11, and that's what we see here, okay? If you wanted to group them the other way, if you wanted to have them set something up like this, you have to actually reformat the data itself. So this is with base graphics, you have to reformat the data. In this case, we can do it by transposing our data frame, and we get it this way, and then we can plot it, and we can go this way, all right? So now we've got 10, 7, 12, and that's plotted here. 10, 7, then 12, and the other group is set that way. So with base graphics, to kind of change the format of our data, or of our visualization, sometimes that involves changing the entire structure of the data itself, which in this case was simple enough with a transformation, but in other cases it can be a lot more complex. Maybe instead of bars, we wanted to use lines, okay? And in base graphics, we could use plot. And when we do this, you will notice a few quirks, okay? One is that we'll see that the blue line runs below the visible range, and that was because the Y range was set when we did our first plot, and when we added the second line, the Y-axis was already set, okay? And then the X-axis is numbered instead of being a categorical thing, okay? So here we go. This is what we see. This is effectively trying to plot this same thing, but as lines, okay? And we have this, 7, 10, 7, 12, and the other one is 9, 11, and I forget 6 or something. But you notice that the blue line runs below the axis, and then the index here it goes 1, 2, 3. But really, it should be. We would probably want it being A1, A2, A3. Okay. Okay. With the GG system, we don't want our data in this form. We would want to turn it into tidy data, right? Tidy data is one column per variable and one row per value, okay? So in this case, we've got a column for A, a column for B, and then the value. And so we have to have our data in tidy form like this. And once we have our data in tidy form, the grammar of graphics works especially well, okay? And what we're going to do, okay, is we map each of those data values or properties of the data to a visual property. So for example, what we want is we are going to use the A value to decide where it goes on the x-axis, okay? So we're going to map the aesthetic attribute of where things are on the x-axis to the values in the A column. We are going to map the color of the bar, the fill of the bar, to the B values. That's what we're going to do. And then the height of the bar, which will be the Y, will be the value of these columns. That's what we're doing. We're mapping the X position to the A column, the color to the B column, and the height of the bar to the value column. That's what we're doing. Okay, and we're going to tell it to draw bars using geom bar. Okay, and that's what we've done. X along the x-axis is determined by the A values. The colors are determined by the B values, and the height is determined by the value column. That's what we've done. Okay, that's what we see here. Okay, we're taking the data in simple.long. The aesthetic mappings are right here. X is A value, Y is value. The fill is B value. That's the aesthetic mapping. We're mapping properties of the data to aesthetic attributes in our visualization. Okay, and then this is to say draw bars, and the stat identity position dodge just adds a few, makes it kind of formatted this way here. Okay, if we wanted to group it the other way, all we have to do is just switch them right here. So what we can do is we say X is the B values and the fill will be determined by the A values. We don't have to change anything in the data, we just change the aesthetic mappings, okay? So exact same data, we've done nothing to the data, but all we did was say now we want the X position to be determined by the B value and the color to be determined by the A values, okay? And that reshapes it this way. So we can go from this to this just by changing our aesthetic mappings of whether we want the X to be determined by the A or the B values and the colors to be determined by the B or the A values. And so does this make sense from kind of this grammar of graphics perspective? We are mapping data attributes to visual attributes or visual properties. We're not actually manipulating or changing the structure of the data itself. Okay, once you have it in tidy form, you can leave it that way and then use the grammar of graphics this way. Okay, if we wanted to make line plots, it's simple. All we have to do, using the same thing, okay, instead of using geometry, the geometric shape that we're going to be plotting, instead of bars, we say geometry will be line, okay? The x position is still determined by the a, the y is still the value, and then here, the color of our line is determined by the b values, and then there's a group property that we're going to have that's going to be determined by the b values here, okay? And this produces this. So, so kind of in summary, it says, you know, with base graphics, we had to use completely different commands to make a line graph instead of a bar graph. And with ggplot2, we just changed the geometry from bars to lines, okay? And we'll notice that when we did the line thing, the range of the y-axis is automatically set to kind of what we're going to plot here. We didn't have to manually specify the range of these things here, okay? And ggplot also automatically generates legends for us, which is nice. All right, so a few terms when we're dealing with ggplot2, okay? Data is what we want to visualize. Geomes are the geometric objects that are drawn to represent the data, such as bars, lines, or points. Aesthetics are the aesthetic attributes, such as the x position, the y position, the color, or the shape points, or things like that. And then we have the mappings, which go from data values to aesthetic attributes. And then we have scales and guides, and that kind of maps values in the data space to values in the aesthetic space, the scale. So the data space, the values might go from 0 to 100, and in the aesthetic space, that might mean going from white to black, or going from red to blue, or something like that, right? You have a scale in the data space, and you need to turn it into a scale in the aesthetic space, okay? Maybe from a thin line to a thick line, or something like that. All right. And guides are how to, you know, show the viewer how to map the visual properties back to the data space, right? So this is like a very kind of like a abstract view of data graphics, right? You know, you probably saw your first bar chart in like 3rd grade or something, but now we're kind of saying, like, what exactly does it mean to have a bar this high? What we're doing is we're mapping something from a visual thing back into a data space in our heads, okay? Okay, so this is kind of a, you know, your typical graphing scenario. You've got data and geomes and aesthetics and scales, and here we go. Okay. And then data types and guides, you got horizontal and vertical position and all of this stuff. Let's kind of flow through this. All right, so some aesthetics only work with categorical variables, such as the shape of a point. You know, whether you're using triangles, circles, and squares, that's probably going to only work with categorical data. Okay, some things really make sense only with continuous, or some things will work both with categorical or continuous, such as the x position. That can be whether it is numeric or not. And then other things, you know, certain things must be numeric and things like that. Okay. We have data must be stored in data frames, and each type of variable that is mapped to an aesthetic must be stored in its own column. Okay, and so that's kind of what we have. All right, so here, let's say this is what we have. We've got the x value, the y value, and the group. This is about as simple as we can get. We've got basically 4 entries of data, 1, 2, 3, 4. These are the y values, 3, 5, 6, 9, and we've got 2 groups, A and B, A, B, A, B, okay? And so if we just create a graph, just saying ggplot, here's our data for our data frame, and we're gonna map the x values to the x position and the y values to the y position, and we don't give it any geometries, it just creates a blank plot like this. Okay, and all that does so far is we've said we're going to map the x value column to the x position, okay? And it hasn't done anything because we didn't give it any kind of geometry. Here we're going to say add geom point, okay? And we get a scatter plot, okay? 1, 2, 3, 4, and 3, 5, 6, 9, okay? And so now we have a scatter plot. If we want to have something about the group variable, we can map that column group to another aesthetic attribute, okay? So probably what would make sense is putting the group, mapping that to the color of our data point, okay? So what we're going to do is we first, there's an interesting thing that ggplot does is you create your plot and you can just store it as P, and then you can add a geom point with this property here, okay? And so it just takes ggplot and then it adds this thing, okay? So now I said take our blank plot here and then add the geometry of point data, and then we are going to map the group variable to the color of our point, okay? Color is spelled with a U because ggplot was written by Hadley Wickham, who's from New Zealand, and so they spell things the Commonwealth way, right? Okay, and that's what we have. Aesthetic mappings versus settings, okay? Aesthetic mappings map data properties to visual properties, okay? You can have settings where you change the visual property, but they are not mapped to a data thing, okay? They're just kind of set universally for all of the points, okay? And so notice over here I say AES as an aesthetic mapping between data and what we want, okay? Here we're just saying the color is going to be tied to the group variable. Over here, this is a setting where it's not an aesthetic mapping. We're just saying set the color to be the color blue, okay? And that's what we have here. This is a setting. This blue is not determined by anything in the data. It's just, we're just telling we like the color blue, so make it blue. I know it's kind of hard to see from your perspective, but that's what we have here. Okay. We can also modify the scales, okay? That is the mappings from the data to the visual attributes. So here, we can change the scale for the x to have the limits 0 and 8, okay? And so all that does is it goes from 0 to 8 rather than kind of what ggplot determines to be a good range there. We can also modify the color scale. So if we wanted to say color is tied to the group variable, so here we're doing an aesthetic mapping between the group variable to the color of our data points. We can change this, the color scale. The default was kind of this, I don't know, this orange and this teal color. And now we can say, I want the colors, you know, this orange, it's a different orange on the forest green, and I don't know if you can really see, but it looks a little bit more goldish, okay? And here we're kind of manually setting the colors that we're mapping to. Okay? In printing, okay, the graphing function in base graphics, the graph functions tell R to draw graphs to the output device, which is either the screen or a file, okay? And with ggplot2, the commands don't directly draw to the output device, okay? The function builds plot objects, and the graphs aren't drawn until you use the print function, okay? As in printing the object. Now, this might feel a little strange, but whenever you give a command to R, what it normally does is it runs its thing, and then it prints out whatever output that we have here, okay? So the behavior at the interactive R prompt is different from when you run a script or a function, okay? So when you run a script, commands aren't automatically printed. So in scripts, if you want to produce your ggplot object, if you want to output, you have to say print that plot. Okay, you have to make a call to it. With ggplot, you might want to transform your data or summarize it before it's mapped to an aesthetic. Okay, so for example, with a histogram, if you think about what a histogram does, is first it does it calculates some bins, right? It calculates kind of a range of values and how many values fit within that range. So it's doing some, it builds up a summary table or a frequency table before it plots the histogram. And so if you want to do something like that with ggplot, you have to tell it to do that. Now ggplot already has like a histogram thing built into it, but what it's doing in the background is it's running the statistical summary part and then mapping the summary values to aesthetic attributes. Okay, so geom histogram will automatically do this for you, but if you wanted to do it yourself, there are stat functions. Okay, I'm going to run out of time before I get to cover everything in this thing. But the full list can be found here. Okay, you go to the documentation for ggplot2, and you can kind of see all of the stuff, part of the tidyverse ggplot2. So make sure you check that out. The basic ones that I'm gonna just kind of, or at least are covered in the notes, are points, lines, and bars. Okay, and then everything else you can look at the documentation. But all of this is, if you understand the idea of mapping something, a column, data attribute in the data, which is basically column, to an aesthetic attribute, then you've got this down. Okay, so with bar graphs, you can do all of this, and check out the documentation, but stat equals identity will use kind of the value that we have here, and so we have this. We can create side-by-side bar plots. You can use a bar plot to summarize counts for categorical data. All of these things. Okay, you can map variables to the color that you want. You can map a numeric variable to the color. Okay, so over here, this is a categorical thing. We took whether it was in the south or the west, and we mapped that to either these two colors. If we want to map a numeric variable, okay, we can map it to a numeric variable. You can arrange them based on the numeric variable here, okay, and so here it's going from least to greatest. And in this case, both the X position and the color is determined by the same variable. And so we're going from darkest to lightest over here as well. And then again, custom colors for these categorical or continuous scales. Okay. Again, all of these things are covered in the R graphics cookbook and the documentation online. So I know I'm flying through a lot of this, probably too fast for you guys to absorb, but the best way to learn is to just kind of play around with it yourself and mess around. So I think I've got some good examples in these things. A lot of these examples are taken directly from the R graphics cookbook anyway. So be sure to check that out. Okay. So we have all of this. You can just map the things to different attributes here. Okay. All right, so we'll end here for today. I'll post up your 4th homework assignment, which will have you do some root finding and optimization and some graphics, and we'll go through that. Okay, have a good weekend, you guys, and we'll see you guys on Tuesday.